Well, let's jump into the talk directly. So, who are we? I'm Rityunjay. He's Alex. We work with the product security team in Citrix, and we do not have interest in very high-level stuff. We are pretty much down to the ground at the grassroots level. So we like breaking into network protocols. We like playing with systems. We like playing with applied crypto. That's pretty much all what we do, right? One critical disclaimer I would like to put: any comments or anything that I have to say or Alex has to say is all our personal comments, nothing to do with Citrix. So please don't blame them for that. And I sometimes wonder, why do organizations do that? Because it also means that the research is not belonging to Citrix, right? That's kind of, but anyway. So today the agenda is going to be roughly like this. We are going to start with where the fuzzing technology and its state is, right? We'll move on to talking about some of the modern code coverage-based fuzzers, AFL being like the top of the list. So we'll roughly touch AFL. We'll talk about what are some of the issues we see in AFL, and specifically when you try and apply that on the network fuzzing domain. And how do we handle this problem in this research? So one of the things we'll be talking about is the definition of gate functions. We'll come to that when we will talk about it. How can a tracing be done at a runtime, and that can feed directly to the fuzzer, and we could use that for optimization. So this creation of a feedback loop, which we'll talk about. We will try and demo you guys a small POC with a toy example, and then we'll try and move into a real-world example. I'll just keep that as a surprise, when that comes. So, fuzzing as we knew it, right? So this is where the whole world of fuzzing started. So a lot of people, when we started fuzzing, I started fuzzing something like a decade back when I used to be with Symantec, and it seemed always like, this was the easy thing to do. All you have to do is to generate a bunch of random packets, send it across to the daemon. Hopefully it will crash, hang, something will happen magically, and you will not believe it, but that time it used to happen. Things have changed a lot. So fuzzing used to be easy. It's not that easy now. Specifically, if you are targeting to do a more targeted attacks, you want to explore certain code paths which is not guaranteed to be covered by just a randomly generated string, or just adding like 1024 A's. That's not going to happen now. So as and when we are trying to target specific functions, like these days, we have seen there are a lot of modular programming. People are doing generated code. So there's already a framework in place, and I need to add a new functionality. I would just go ahead and use that framework and generate some additional code and add it there. Now, if I want to do a targeted fuzzing for this thing, it's kind of difficult for me to do that just by random packet generation. So another challenge which we face is that during random packet generation by using generation or mutation or whatever, you end up having a lot of test cases, a lot of packets which just get dropped. It really doesn't cross the basic threshold. So doing effective fuzzing, which could actually test the product or target the vulnerabilities which we actually want to be targeted, it is not trivial. Well, in the world of fuzzing, I think one of the first things that started happening was when people started researching was to look into file fuzzing. And there is a lot of focus which actually went into it. So AFL, HonkFuzz from Google, some of these are like pretty strong examples of this area. And I think AFL, I'm personally very, very impressed with. Now, the ideas which these guys used was pretty good. Unfortunately, using them on the network world is getting a little tricky. We tried doing that. We're not very successful. There were some hacks you could try. So I think I'll let Alex talk about some of those hacks. But it's tricky. In the network fuzzing world, we were still stuck with modeling of protocols. So if I really want to write a very exhaustive, good quality, in-depth fuzzer, first thing I have to do is I need to go through a documentation of that protocol if it's available, if at all it's available. And the documentation would be like some 200 pages of PDF file, right? And at bunch of places, they will refer to another document, which is another 200 pages, right? Frankly, I am an engineer, and I don't have the patience to read the documents, okay? It's a weakness I have. Sorry, I'm sure many of you share my weaknesses. So it's really difficult for me to go through and analyze all these documents, write the fuzzer accordingly. And even if I do that, I don't have the guarantee that I'm really covering what I'm expecting to cover. Am I really unearthing the vulnerabilities? So modeling of the protocols, this is still, and the network fuzzing in itself is quite slow because we tend to face some very practical problems like synchronization, right? How do we know that when we send a packet to the server, should we be expecting a packet back? Should we not be expecting a packet back? Not getting a packet doesn't mean the server has crashed. There's a lot of uncertainty. So inherently, network fuzzing doesn't go as fast as file fuzzing. Another thing is that we always have a need for setting up an agent which sits on the server side, which can keep detecting the crashes, do some sort of a logging to identify what crashed, where, what happened. So that is also another challenge we always face. Bottom line, when it comes to a 600-page of documentation of the protocol, we always end up doing a blind fuzzing. At best, we will take stuff from the Wireshark, we'll take the packet, we'll do some mutation, and we'll send it across. Little less blind, all right, but not very great. So it's like with some specs. I don't know. What is interesting to see is that network stack still happens to be the target of choice. There are still so many network protocols out there, so many ports open on so many places, and we still want to break that, right? So what we are looking for is a little more balance on the network side and not just on the file side. So just trying to sum up things. So historically, what we have seen is there have been usually two kind of approaches which have been most successful. You either do random byte flips with some sort of mutation like what Peach does, or you could do some modeling of the actual protocol. Again, what you can use any other frameworks to do. Bottom line, you end up running millions of packets, and all you feel is that, yes, I have run like, say, 100,000 test cases, and I could go and tell my VP that, you know what, I did this. My VP feels good about it, that yes, you have withstood 24 hours of fuzzing without crashing, and yes, the product is secure. Is it really? Well, we'll see. So I'll let Alex take over from here and talk about some of the recent advances and what we are doing.
Thanks, MJ. So yeah, I'll be talking a bit about how we do fuzzing today. Mostly, can you guys hear me?
Yeah, I think it just turned on.
Sure.
Just keep it in hand. Sure. Here.
So yeah. So I'll talk about how we do, fuzzing today and the, the improvements which have been made over, what MJ was talking about, the blind protocol fuzzing, just flipping bits. So, today, there's been some concepts introduced in fuzzing, through genetic algorithms, basically, where, the idea is you want to retain only the best input, and you want to be able to measure how much impact an input has on your target, right? So today, we're capable of knowing that when you send a particular input, you're going to know the effect it has on your target binary, right? You're going to know if it's valuable or not. And through these genetic algorithms, basically, you're going to elect basically a bunch of species of inputs, which are the best portions of inputs that you have to play against your targets. So the general idea is that you mutate your best set of inputs, you send them to the target, and then you measure, what's called fitness based on some heuristic I'll talk about soon, which basically gives you feedback. Is this input valuable? Yes, no. And basically you take a decision further based on this, right? And then you discard or prioritize the input. So now we live in a world for, file format fuzzing and to some extent simple network fuzzing, where basically how valuable your input is to the target, right? Which is fantastic, basically, because you're not blind fuzzing anymore. So generally, what fitness function can you use? The general used one is code coverage, right? So why? Because basically, code coverage tells you exactly, what are the extra paths that you've triggered based on your input, right? So basically, it tells you how good it is or bad it is for your target, how much code it has executed based on that input, right? And so most of the tools out there are able to measure code coverage, right? And that heuristic allows you basically to take a good or bad decision, based on historical data. So, you can achieve this, by doing, by binary instrumentation through PIN or Dynamo REO. We took the option of using PIN for this. You can do a bunch of static rewriting, kernel probing, or to some extent, even the hardware can do it now today. So how does this work? So the general idea is that you're going to model control flow using basic blocks, right? So if you guys have open IDA Pro or IDA, you're going to have a graph with a bunch of blocks, right? So the idea is you do exactly the same thing at runtime, right? So you're going to disassemble and basically, have all blocks of code which do not modify control flow segregated, right? So this tells you, and then what you want to do is count the number of edges you have between those basic blocks, right? So if you see the orange arrow I put there, that's a transition from one basic block to another, meaning there was a change in control flow, which means that, in a programming language, an if statement has been taken or something like this, right? And so the thing is, when you retain the edge count between basic blocks, it gives you a big set of unordered code coverage map, right? And the thing is with sets is that they can easily be compared. So you've got this gigantic set based on your input of what code coverage has been achieved. And that's in a set which you can easily compare, right? So most of these evolutions come from way back, but all this was kind of industrialized through AFL, right? So again, AFL is amazing, right? An amazing tool. It's a battery included fuzzer, so it takes care of all the building, all the instrumentation, the minimization of the corpus, and all this kind of stuff. So it's just brilliant, right? Because it's got this perfect balance between using the power of the build system, through make or CMake or whatever you want, speed, through the fork server and all this stuff, and through functionality. The only caveat it has is that basically AFL by design is meant to compare traces across runs, right? So it means that you run your target once, twice, until n times, and the map comparison happens when the target exits, right? So the comparison happens across execs. So this means that for network daemons, it's a bit more complicated, right? And I'll talk about it a bit later. Also, AFL has to get its data off stdin, or off a file descriptor, right? Which is directly passed into the target. So again, I'll talk about the limitations we try to address, but if you understand what I was just talking about a second ago, the requirement that your target has to exit can be complicated basically for network daemons. So again, if you've got source code, again, we're not trying to replace what AFL has done because it's still the best option out there, right? If you have source code, just get it to work on packets, right? You can do it. It's a lot of work. You basically have to write some code, write some wrappers, right? Handle most of the state, make sure it exits after its main event loop and all this kind of stuff. It's not pretty, but it can work, right? The problem is if you've got very tight coupling between the code, basically, which handles network packets and parsing, you're going to have to stub out a whole bunch of stuff, right? By stubbing out, I mean that all the network calls you're going to have to mock, in a sense, right? Meaning that you're going to have to LD preload stuff, which means redefine the way that recv, for example, works, read and write and accept and all this kind of stuff. And this is, Preeny does that if you guys have worked with it. Or you can use a bunch of linker tricks. So all this basically to say that, for network daemons, what we'd like is, to keep the successful AFL concepts or the genetic algorithm concepts, as well as the code coverage feedback, but avoid restarting the target, right? Because this would allow to get these maps at runtime, right? The thing is, it breaks the deterministic nature of AFL. So again, We want to improve upon the traditional fuzzer, so break the cycle of like, I'm going to send a packet and I'm going to then probe to know if my target has crashed, or I'm going to ask my agent to know it's crashed, which is quite slow. And by borrowing all the advanced features from feedback-driven fuzzers. Again, you want to do this during runtime and without respawning the target between inputs, right? So our approach, we did a bit of work around this, and we tried to at least start working on this problem. So it comes, basically we observed and just thought about how network daemons work, right? So generally they're going to do a whole bunch of startup stuff, which you don't really care about, right? It's going to read a config file, it's going to initialize a bunch of stuff and all these things, right? And then it's just going to wait for a con, right? So it's going to hang on an accept call or something different for UDP. And then it's going to basically read an input. And from there, it's going to get a buffer of bytes it's going to want to work on and parse it to make sense of the protocol and what's happening, right? And based on that parsing, it's going to take a decision, write back something out to the socket, an error or some validation. So in this context, basically, what code coverage do you exactly care about? Well, you can kind of simplify this and discard everything, all the initialization stuff, just chuck it out the door, it doesn't matter. But the interesting stuff generally happens between the first read on the network and the write, right? So the whole idea here we're going to talk about is, can you get those code coverage maps triggered during the specific syscalls? So to generalize this, you can call these read and write syscalls, gates, right? When you enter a gate syscall, you'll start the tracing, right? And when you exit the gate, you stop the trace. So the idea is that you're going to monitor a bunch of syscalls at runtime, and when you hit one, you start the trace. When you exit one, you stop the trace. And the idea is you're going to dump that trace and give it back to whoever consumes it, fuzzer, reverse engineering stuff, or whatever, it doesn't matter, right? And you transfer that code coverage back to the decision maker, right? Which can take then an intelligent decision based on this code coverage data. So again, you can generalize this a bit further, right? So the idea again is, all this is only about code coverage, right? We don't bother about all the fuzzing stuff because the mutation can be done by anyone at any time. And so based on a defined gate syscall, say X or Y, you can, again, when you hit X, trigger code coverage. When you hit Y, stop it, and then dump the trace. So this can be achieved pretty much for any syscall out there which has a relation, right? So this 1,000 feet view of this is you want to only track file descriptors, right? Because they're the ones who tell you when the data is valuable. You want to ignore, right, all the I/O happening. So you don't want to care. You don't want to start tracing when something reads a file or when something's like that. You want to generate the hit map at runtime only when the gate syscall are hits, right? And again, as I said, dump it to the fuzzer further. So I'll take the example of TCP here and how you can filter file descriptors for TCP, right? So the accept syscall, it basically returns a file descriptor, right? That is then going to be used further for read and writes, etc. The syscall layer. So if you hook into the syscalls and just look for anything for the accept and instrument it and get the return value of accept, basically, you can build a list of file descriptors you're interested in without polluting that list with stuff from the I/O layer, right? And so then you've got that list of file descriptors which you know are from the network and which you're probably going to be interested in. And then you also instrument read and write, and you figure out when read receives the argument of the file descriptor which is in your list, then start the trace, and when you hit write, just ditch the trace, right? So here I've got a silly example, right, where file descriptor 6 is good for tracing and 9 probably comes from the the I/O layer, and we just junk it, right? So another interesting point about this kind of gated syscall analysis is that your coverage maps are per read-write gate, all right? So if you've got a connection which has many gates, which is generally the case, right? You have a bunch of exchange, and you're going to have a read and then a write back and then a ping-pong kind of exchange for the protocol to happen. Well, you can get the coverage map for each gate, meaning that you can enter the protocol at different layers at different points in time and get the coverage map for that specific packet. But it also has, if you remember what I said, is that those code coverage maps, they're sets basically, right? So you can also aggregate them if you want to have a macro view across multiple gates. So this is the 1,000 feet view of how the pin tool works. So as I said, it hooks a bunch of syscalls, right? Basically all the networking syscalls. So accept, read, write, close, receive from, send to, all this stuff, send message, and so on accept. Add the file descriptor to some list of stuff you're interested in, a whitelist of file descriptors, and track it across the further syscalls, right? And then you can see my little heat map there, which is basically what I was talking about before, which is the edge count per basic block, right? And you can see that on the final write or the final close, basically that heat map is flushed out to something. So for UDP, you can do basically exactly the same thing, but track different syscalls, right? This worked exactly the same. Right? And again, I just want to say this, that it's generalized, you can generalize this to any possible sequence of syscalls. And you could come up, as something, a grammar basically to describe this and have runtime code coverage information based on some whatever runtime criteria you believe in. So we wrote a simple pin tool called netcov. So its only job in the world is to do exactly what I said. It's basically to generate the code coverage map based on the runtime data, right? And all it does is that it waits, it does exactly what I said, and it will write the output to a pipe, right? So it will flush out the code coverage map to a pipe where it can be consumed by something else. And so basically, it's the reverse kind of the fuzzing talks, right? Where, before people used to say instrumentation is up to you, right? All this stuff. Well, here, basically, the fuzzing is up to you. All you get is that when you send an input, the code coverage which happened. It's got a sidekick called netCallGraph, basically, which just generates a runtime call graph. So on the same principle of this, those gated syscalls, you can generate a runtime call graph of what's happening. So it can give you some interesting insight for reversing all this kind of stuff. And I've got a really simple dummy, fuzzing example that I'll go through a bit later, which shows this. So again, the point of all this is just to get people, trying to think about network fuzzing and get interest basically in it. So it's a POC. It works relatively well, but again, it's got a bunch of limitations, right? So it doesn't work for select poles. Even though it could be adaptable. There's no crash detection, but I mean, that again is a solved problem in the pin world, so it wouldn't be very hard to achieve. The more complicated one is there's no address sanitizer, right, to catch out-of-bound reads or writes. So that's a bit more of a problem. There's some work, in the pin community to get address sanitizer like tools within pin tools, which could be adapted here. And right now, the heat map or the hit map format is basically text-based. It's completely not optimal at all, but it kind of works. What it works very well with is multi-threaded daemons, right? Because it will work across forks. It will work with pthread and all this stuff. Because file descriptors happily are shared between parent and child. So all this stuff works for multi-threaded applications. The interesting thing also is that heat map is per file descriptor, right? So it allows a form of concurrent fuzzing, meaning that you can have multiple instances of those guys and just do selection based on the file descriptor that it happened. And well, by design, it's mutation independent since it doesn't do any. And since it's a pin tool, it's source code independent, right? You don't need to build anything. You just dump a binary in it and it just runs it and does some stuff. And it's slow because it's pin. So again, the netcov flow. So you've got a client, which is a fuzzer, and you can see that the orange lines basically show, the protocol exchange with a daemon, and then the red stuff is the coverage map returned by netcov back to your client. So I'll do a super quick demo here. So I wrote a super, a silly daemon basically, which if you can see the code, it just looks up for magic, characters inside a buffer, right? So it's a bunch of nested branches just to show my point that code coverage increases, right? When you send the right value at the right spot. I'll try and put this here. So. Sorry? Oh, yeah. Oh, yeah, but I won't see it, right? All right, so here, I just started it on the dummy program I was talking about. And here, I'm just going to listen out on the pipe, right, and see what happens. So if you just echo something back into it, right? Right, if you just echo something back in, you'll see that here it spit out some stuff, right? So this is the code coverage information when you send this particular packet, right? No, I need that. No, I need it. All right, so again, if you just send the same thing, here you can visually see basically that the code coverage doesn't change, right? The edge count is constant, right? So if this was a fuzzer, basically I'm a manual fuzzer here just doing some stuff. If I add an A, randomly by having lack of byte flipping stuff, here I should take an extra branch, as I was saying, and basically you see the code coverage increases, right? So the whole point of this is just to show that here you get feedback at runtime for this kind of stuff based on network connections. So again, if I put a B, I'm going to take a new branch, etc., and all this stuff, right? So here's just to give an example to visualize what's happening and to see the code coverage map increasing. One other interesting thing I want to show you is that I added one parameter which basically is used as a loop boundary. So here, the last parameter 3 basically is used as an upper loop boundary, right? And what happens is that you're going to see that inside the coverage map, you're going to see that edge count increases. So you can know also when you're controlling the upper bound of a loop boundary. Right, so if you look at this, I know this is a bit abstract, but basically here you're going to see this number 3, which will probably change, meaning that you're controlling a loop. So if I change this to 15, for example, it should do more iterations on that edge. Oops. So again, you can see here that hit count increased. Right, so it's just to show that you can also have fine-grained control and view actually that edge count increase, and when you control the top of a loop boundary. Right. Let me get back to the slides. So I just wanted to show a quick example of the net call graph stuff I was talking about. So this again is something which was drawn at runtime. So if you look, basically this is a view of that dummy daemon between a read and a write, right? So these are the operations it does. So you can actually visualize this stuff and dump it out if you're interested in doing this. So I wanted to show the process. Basically, I showed you the manual fuzzing stuff. So I wrote a very, very simple fuzzer based on this, where it's just the Charlie Miller algorithm, where you just basically byte flip random stuff, and you want to see it increase in the code coverage, right, and start finding the correct inputs. So I'll just show this very quickly. So this is my very simple fuzzer, which is going to get some feedback. Right, so what's happening here is that the fuzzer is just trying a bunch of random mutations. Right, and it will take its time, but eventually it should be able to byte flip the byte we're interested in and start finding code coverage entries. If this takes too much time, I'll just skip it. But basically, you should see this guy, suddenly when it finds the right input, that will start basically finding that the hit count has changed and increased. All right, so since we're running a bit out of time, I'll just skip this. Okay, so all this to show that like we can have probably better tools for code coverage and for fuzzing network protocols. There's probably some evolution we can work on here to get similar technologies that are used for file parsing can be applied in the networking world, and hopefully that can help us find bugs quicker and mostly be more efficient at fuzzing this kind of stuff. So now I'll pass it over to MJ, who'll talk about a real-world example, basically, based on the RDP protocol, and he'll quickly discuss, how reverse engineering and the fuzzing portion of this, are tightly integrated and can work together. Thanks a lot.
Thanks, Alex. All right, guys. Referring to something I mentioned earlier, if I could just kill the whole idea of reading my documentation to assess what the packet structure looks like, and I could get a fuzzing ready information about the packet, I think that's good enough for me to write a fuzzer. So what we were trying to do was to see that for the RDP protocol, and RDP I think everybody knows about it, right? So for the RDP protocol, is it possible for me to extract the packet structure using the feedback loop and come to a level where I may not know what each byte represents, but I should have a fair idea how to fuzz that byte, right? So that's the kind of demo I'm going to try and do here. Hopefully this will work. So, all right. So RDP is our regular Windows remote desktop protocol, and that runs on 3389. It has a lot of variants on the Linux world now. There's a XRDP, which you can find on the Unix environment. And RDP clients are available practically everywhere. So it's kind of a nice protocol. And frankly, some point I want to hit a CVE on this one, but let's wait on that one for a moment. So this is what I did so this is a small POC around netcov, how it can be used. So at a high level, what Alex was telling was how the netcov binary tracing works on the server, and it puts all the data in the pipe. The pipe name over here is temp netcov. And from there, the binary trace, which is basically between the receive and the send system calls, this is given to a fitness function. Like any genetic algorithm, you will have some heuristics around it. So the heuristics that right now is being used is just the count of the number of edges which is being covered. So yeah, it's not the perfect one, but then it just gives an idea of how many edges have we been able to cover. Now, that is a fitness function which kind of sends back the feedback to my client side. So this dotted line basically divides what's on the server and what's on the client. On the client side, I get this information. Based on that, we modify the mutation strategy, and the packets will be mutated accordingly. So everything which you see here, the rest of it is pretty obvious, except the input is something which is read from a Wireshark trace. So just to make life simpler, you can put a Wireshark somewhere, take RDP connection dump, put it in this tool, and it will automatically generate the packet structure and give it back to you. So if I have to use this whole tool a little differently, maybe to do fuzzing, to improve on some heuristics, it's the green boxes which I need to play with. A better fitness function will typically give you a better result or something. Similarly, based on that, the mitigation strategy will have to change. Right now, all I want to do is to understand the structure of the packet. So it's basically reverse engineering the protocol, the packet structure. If I want to do fuzzing, the strategy has to change a little bit. One of the biggest challenges that usually, I faced with this whole automation, and we were struggling with that a little bit, was a synchronization problem, because you send some packet, you don't know what packets to receive. Sometimes it just goes out of sync, packet drops, all kind of things. So I'm not going to go in details on how to solve that. That's more trivial engineering. So let me just quickly do a small demo, and let's try and see what we are looking at. All right, so I have set up a small shell script, which basically so all that this guy does is that it kills off any RDP which is running, and then just attaches the netconf client that we were talking about here, this tool. It attaches this thing to our XRDP binary. And there is a flag to it with a -m here, which basically marks out which is the module you want to trace for fuzzing. So usually in the real world, they're going to be like 10, 20 modules which are dynamically linked. And if you start tracking each one of them, you could actually end up with a lot of graphs which you really don't want to analyze. That may not even be the code which you're looking into, right? So you can actually choose which is the binary you want to look into the trace for. Over here, it is libxrdp, which is the one I'm looking at. And that's what it's going to do. All right, so the attach has been done. That's good now. All right, the server program basically over here collects the data from this pipe, where the output will be written from the trace, and it's going to analyze with the fitness function. And this is the guy who's going to send the trace back. So that is fine. And the final part of it is our, so this is the analyzer. So what we have done is that this is the pcap file which it takes as input. And typically, the pcap file can be taken anywhere between any client and server. And you might want to target something else. So a small thing I added was to just to mark which is the IP address which is acting as a server in the pcap file, and what's the target, right? So they can potentially be two different IPs. So what this basically does is, the small thing which we are doing here is that for each byte, so this is the first packet which you are seeing here. And if you see, the byte which is being flipped right now, it just serially goes from one byte to another. And what it does is that for each byte, it takes the value as 0x01. And in the next iteration, it takes 0xFF. So what we want to do is to enable all the bits or disable the bits, and see if that changes the control flow somewhere. What also, if you see a little bit here, is that at offset, over here the control flow changed. We were able to go deeper into the code, and so after all, let's say if you have a 30-byte payload, what you were talking about is 60 iterations of that packet. So 2 iterations per byte, and we get an idea of what it looks like. And then it's all about a little bit of massaging, but the final result that's it. So the packet structure that it looks like is something like this. What does this really mean? Let's just try and look at that for a moment. So coming back to the, so when I send this base packet, this is roughly what our baseline looks like. And this is something I forgot to show you guys. So if you see in the trace here, for each packet, this is the trace which is coming in. So if we go right at the top, we will, let me just show you that one trace. So if you see here, the first byte, byte 0, is a control byte. A control byte basically implies that this is something which is changing the control flow somewhere, and we are probably expecting a different code coverage than what was there earlier. So, and that's pretty obvious based on the coverage length here. This is the coverage length, and usually the next byte, which is a data byte. So you can just see the size of it, right? How different is this? Just visual inspection can tell you that there is a code flow difference. So coming back to the slides. Yeah. So at a high level, this is something, we are using the same text-based format on identifying the code coverage. The results which actually we got is something like this. So what I wanted to do was to take a look at the XRDP protocol specification. I didn't go through the whole 200-page document, but yeah, a few pages is okay, right? So what's interesting is that if I have to understand if I'm getting the results properly or not, I wanted to verify that with the first, first 5, 6, for the first 6 to 7 bytes, that should give me a fair idea whether we are going in the right direction, right? The rest of it is data. So this is the RDP specification. So what I'm primarily interested in is in the T-packet header, which is a 4-byte thing. And then there is a X24CRQ, which is 7 byte, after which there is a lot of variable field. So that all goes in data. I'm not too worried about that. But primarily it's the first 11 bytes which I want to look at. So let's take a look at the first 4 bytes for a moment. So this is the T-packet header. The first octet, which is the first byte, it basically talks about the version number. And the protocol is different based on this binary value, which makes sense because our first byte did actually turn out as a control byte, and it was actually changing the direction of the flow based on what this value was, right? Logically, makes sense. The second octet is basically a reserved byte. Nobody really uses it today, so it kind of just goes off as data. It doesn't change the control flow, which is exactly what we found. The next 2 bytes turns out as the packet length. It's interesting because what we are doing right now is just a simple mutation of the packet, and therefore the length of the packet really doesn't change. And also it's interesting to see that these 2 bytes is turned out as a magic here. So when I say something is a magic byte, it just implies that if you flip this byte, the packet will be dropped, right? So basically, if I have to make a rough assessment of what I have learned till here, is that there's a very strict verification of these 2 bytes, and they verify whether the packet length is exactly matching this value or not, right? Something that I could learn just from this much. Let's move ahead. The next set is the first byte, which is the byte number 4 here, actually byte 5, offset 4. That's the length indicator field. That's another 1 byte length thing, but interestingly, this is the length for this header only, and it could potentially change because there are a lot of data after that. So this still acts as the data. It doesn't change the control flow anywhere. The next byte 2 is basically broken into 2, so the byte is broken into 4 bits each. It has 2 different control structures in it. So that specific byte is still a control byte, and the rest of the thing is set to 0, or it is referenced in something, but eventually that is not something which is changing the control flow. Well, I feel good about it after doing this analysis. So because now at this stage I know that from the first packet, the mutation of the first byte is going to lead to a change of control flow. 3 and 4 are going to be a length field which should not be played with. unless you are actually going to change the length. And it is also sure that they are verifying this length. Now, byte 5 is something which is also length, but they are not really enforcing it somehow. So this is a place which could actually potentially lead to some kind of overread or underread or something. I would like to play with this one, frankly. And byte 6 is another control flow, and byte 7 to 38 is all data. What this implies for me is that now I don't have to fuzz this in a linear way where I could fuzz one byte at a time, but I could differentiate all the control bytes together and all the data bytes together. And this is basically the product of the number of use cases which I want to fuzz. So for each control byte mutation, I could choose all the mutations of the data byte, and I could potentially reach to a different location. Make sense? So with this kind of information, who in the room cannot write a fuzzer? Right? So I'm not going to do that. So just for a conclusion, let's take a look. There's a lot to do in the network fuzzing world, and what we have just talked about is just a glimpse of what can potentially be achieved by this technique. This is just to invite the community to start playing with this. And yeah, that's pretty much it. Thank you. I'm open for questions.
A few questions? Yeah. Does anybody have any questions for our speakers? If you do, come on up and get the mic.
Not having questions is never a good sign. So I was really in a bad accent today.
All right. Thank you, gentlemen.
Thank you. Thanks a lot.